Okay, so in the previous video, I showed you how to estimate those parameters, beta 0 and beta 1 on Excel. So we will take those numbers first, and before looking at the numbers, I will give you the basic properties of the point estimators. So in chapter 8, in the chapter about estimation, I gave you two basic criteria for a good estimator. That was unbiasedness and efficiency. Unbiasedness was associated with the mean, and the efficiency was about the standard deviation or the variance. So now we have there is a mathematical theorem for this, but I'm not going to show you the theorem. There is a proof, but I'm not going to show you. But you can just believe that. Just believe me. The estimators calculated by Excel are unbiased. They are unbiased. Of course, they are good. And second, also there is another theorem which is proposed by Gauss, the famous mathematician. Gauss showed it. So the estimators are efficient. The most efficient estimators among certain regular estimators. So of course, you can make up a very strange and special estimator in a special case that could be more efficient than the estimator, but that is very exceptional. So among just basic, regular, standard estimators, the Excel estimators are the most efficient ones. So combine these two results, Gauss called the estimator as the best linear unbiased estimator. So we call this blue theorem, best linear unbiased estimator. Taking the initials, BLUE estimators are what you get from Excel. And let me show you on Excel. So I increased the font size to help you see that. Here, this part is the point estimators. So intercept beta 0. Beta 0 is estimated to be 8.189. And output, the coefficient of output is 2.383. So those are beta 0, beta 1. Fixed cost and marginal cost are estimated by those two numbers. And as I said, those two numbers are unbiased and most efficient. So they are best estimators. There is maybe many textbooks have include the theorems and their proofs, but I'm not going to show you. So we take those two. We learned what those two numbers mean. They are pretty simple. And next, the standard error of the regression is related to the error term. Of course, this is an error term. You want to have a smaller error. So if the error size of the error is small, then of course you can do a better inference. Your estimators will be more accurate. So the size of this error matters in your statistical inference. So what the size of the error is the standard deviation of the error term, because the error term by construction must be mean 0. The expected value of the error is 0. So that's the nature of an error term. But so its size is not determined by the mean, but by its standard deviation. So the larger standard deviation means the error could be a big number to the negative side or to the positive side. Or if the standard deviation was small, then the error will be overall pretty close to 0. So overall error is small. So estimating the standard deviation of this error term is important for the accuracy of your regression analysis, right? How big your data includes errors or noises, right? So we call that the standard error of the regression. standard error of the regression means the standard deviation of this error term. And that's calculated this way. You don't need to memorize it, but idea is simple. Here epsilon should be estimated. It's not that difficult. Once you estimate beta 0 and beta 1, you observe x and y and x are observed. Beta 0, beta 1 are estimated. You know them as like by the point estimators. Excuse me. Then automatically you can calculate epsilon. So use that as an estimator for the error. And we know the mean is 0. So the deviation, usually when you calculate standard error, standard deviation, you have to subtract the mean, but we know the mean is 0, so you don't need to do that. And then square. So we calculate squared deviation. So the same square, taking the same step, taking square and then sum and divide by the sample size minus 2. Here, the major difference is when you calculate the variance, the sample variance formula was n-1 divided by n-1. But now we have n-2. So the reason is now we have two parameters. This is so when you calculate the variance, you took 1 off in the denominator because at that time you had to calculate mean. So calculating mean and subtracting it from the observations consumed 1 degree of freedom. We call that you can think it as information. It consumed calculation of the mean consumed 1 information. So we are using as if we are using n-1 observations conceptually. But now to calculate epsilon, you consumed beta 0 and beta 1. That is, you are losing 2 informations already calculating when you calculate epsilon. So you are using as if n-2 observations. So you can think that 2 observations are consumed in estimation of beta 0 and beta 1. So you subtract 2. So the intuition is pretty much common. Like later when you have more than 2 parameters, then you subtract more. That's the idea. So we call this the degrees of freedom. So after you consume 2 informations to estimate those 2 prior parameters, then your degrees of freedom is only n-2 because n is the sample size. You consume 2 of them. So that's how we interpret the intuition behind this denominator, right? Then back to the table result. This is the sample size. In our example, there are only 12 observations, monthly observations, and this standard error is calculated to be 1.7164. So the standard error of the error term is estimated to be 1.7 something. So and the 12 is the sample size, and then in our analysis here, the denominator must be 12 minus 2. So 10 must be in the denominator. So okay. So the inside the square root is the variance of this error term. And when you calculate the variance, right, remember, we calculate the squared deviation and divide by sample size minus 2, degrees of freedom. So basically, it's exactly the same steps as you calculate the variance of a random variable, right? And so that was about estimation. Now, how can we... so now we are going to think about the standard error of the point estimator, beta 1. Remember, by just to remind you, when we estimate the mean, the population mean, then the best estimator was sample mean. And then we had to calculate the standard deviation of the sample mean because this would be the standard deviation of the sampling distribution. We use the center limit theorem. Then we need the standard deviation, and that was given by this. So numerator is the standard deviation of a single variable, and the denominator was square root of n. That was the result that this was used to calculate the sampling distribution of x bar in chapter 7, maybe, about the sampling distribution. Now, we have a similar structure, but it's slightly different. Basic idea is simple, but first, the denominator is square root of n minus 1, not n. The idea is the same. There is another parameter, beta 0 is another parameter, so you have to lose one, you already consumed one information, save one information for beta 0. So you are taking n minus 1, right? You use n minus 1 in the denominator. So at square root of n minus 1 plays the same role as square root of n. And the numerator includes standard deviation of epsilon. Basically, this is the same role as this one. So underlying randomness is standard deviation of epsilon, right? And then what is this guy? So its standard deviation is, this part is divided by standard deviation of x. The reason is because beta 1 is multiplied by x. So what you calculate is, so you can think this part, standard deviation of epsilon divided by square root of n minus 1, can be thought of as the standard deviation of the whole term, beta 1 times x. So this part, you just calculated the standard deviation of this part. But what we need is just beta 1, only the beta 1, not x. So to remove the multiplication of x, you have to divide it by standard deviation of x. Then you can isolate standard deviation of beta 1, right? Right, that's the intuition. Of course, its derivation would be much more complicated, but I'm not going to show you, but I want you to get the idea, the intuition, and the similarity between what we are doing now and what we have done in an earlier chapter. Okay, so then this standard deviation for an estimator, this is a standard error of an estimator, that is here, right? Anyhow, you don't need to remember the formula. The numbers will be calculated by Excel or any kind of software, but you just need the intuition, basic intuition, how it's calculated. So then you can think it this way. So the intercept, the fixed cost was estimated to be 8.189. And how accurate it is captured by the standard error. Similarly, beta 1, the marginal cost of an output was estimated to be 2.383. And its accuracy was measured by its standard error, 0.206. So, and these numbers are calculated by this formula. And here, standard of epsilon, standard deviation of epsilon was this number, standard error, excuse me. So this number is used, standard error of the epsilon of the regression is used to calculate these guys first. And of course, the sample size is used in the denominator of these guys. And then standard deviation of x can be calculated from the data. That's not that difficult. Simple. Okay? So we learned what these are, and what these are. We are taking down some part of the output, the results. And then when you can calculate the standard error of the estimator, then we can use them for the sampling distribution. And we know the same intuition holds here, that in the end, approximately beta 1, the point estimator will be approximately normally distributed by the center limit theorem if the sample size is large enough. even though our example only has 12 observations, so actually this assumption is not true, but okay, just just assume that the sample size was large enough. In practice, like you are going to use a larger data set, so it's not a big problem. Anyhow, the same machinery holds here. We can show that mathematically, we can prove that the sampling distribution of the point estimator is approximately a normal distribution, and the mean of the normal distribution is the true parameter, and the standard deviation was what we calculated in the previous slide, right? So we learned the normal like the random error in your estimation error will be normally distributed, and we use the same like procedure as we derive the confidence interval in an earlier chapter. So in an earlier chapter, remember, this is what we obtained from the normal distribution, from the sampling distribution. And at that time, your point estimator was x bar because you are estimating the population mean, and then sample mean is your point estimator, and you have to allow plus minus margin of error. Margin of error depends on z value, something from the normal distribution, standard normal distribution, times the standard error of your estimator, point estimator. Your point estimator's standard deviation is this part. So now in the linear regression model, structure is identical. Point estimator is beta 1 hat, and the margin of error takes this form and identical. So z alpha over 2, this part is the same, and standard deviation is the same. Standard deviation, of course, its calculation, it is more involved to calculate the standard deviation of beta 1 than x bar, but still Excel is going to do that, so don't worry. And Excel is going to calculate this formula instead of this, so it's not a big problem to calculate this. But once you have it, confidence interval is the same formula as we learned in an earlier chapter, so not a problem. And then you find it here. These numbers are calculated based on the point estimators plus minus margin of error determined by the standard deviations of the estimators and confidence level of 95. Of course, if you change the confidence level, then those numbers would be different. But also you know how to do that. Instead of 1.96, you can change the numbers to like 2 point something, 1.64 something. Okay. And then the next step is to do a hypothesis testing. So as an example, to do a hypothesis testing, we have to set up a hypothesis. In regression analysis, usually the hypothesis is 0, unless you have some other hypothesis to test. Usually the first hypothesis testing is around 0, is about 0. So this means if beta 1 is 0, that means x and y, when x increases, y does not increase. That means those two variables are irrelevant. Change in x does not change y. So if this is true, that means two variables are irrelevant. That means your regression model is pointless. It's useless because you are trying to predict something with an irrelevant variable, right? So this hypothesis test is a common, usually the first hypothesis testing, very important testing in the regression analysis. And then, given this hypothesis, it's two-sided, two-tailed hypothesis, then the t-statistic is beta 1 hat. Originally, you have to have, look at this first. The t-statistic was like this. That is, your observation is x bar, and mu 0 is what you believe. What you observe and what you believe, and their difference is standardized. That was how you calculate the t-statistic. We are doing the same thing. What you observe from the data is beta 1 hat. Beta 1 hat is what you observe from the data, and what you believe is 0. So the difference is beta 1 hat minus 0, but of course minus 0 disappears. So numerator is, the difference is beta 1 hat itself, right? And then it's standardized again by the standard deviation of beta 1 hat. We know how to calculate that. We calculated it already. So the same structure. Denominator is the standard error. Denominator is the standard error. Numerator is the difference between the observation and the hypothesis. Observation and the hypothesis. Okay? And then once you calculate the t-statistic, then p-value is the same, because anyhow you are going to apply the standard normal distribution to the t-statistic. So p-value is the same as long as you consider two-sided hypothesis testing, right? That's calculated in here. These hypothesis testing. So this t-stat and this p-value, the upper ones, the upper pair, t-stat and p-value are for the intercept. It tests, this is the testing result, the t-statistic, based on the assumption that the hypothesis that the intercept equals 0 or not. So you are testing intercept is 0 or not, then the t-stat is 6 and p-value is 0. And if you do another test, whether the coefficient is 0 or not, then t-stat is 11, p-value is 0. Then let me ask you this question. So of course, Excel tells you the p-value, the t-stat and the p-value, but it does not say whether you reject it or not, because that depends on your significance level. So now I'm going to consider the significance level of 1%. In this case, can you reject the null hypothesis that the slope of the output equals to 0 or not? So can you reject it or not? I'm going to give you the answer in the next video, and I will bring a real data set to apply the linear regression analysis. So see you there, and try to think what's the answer to this question.